Okay, welcome back everyone. Nick Russo here, and we're on to our second component of the model known as deoptimization. And again, the reason I'm using the word deoptimization is just so it has a negative connotation, which means our goal is to reduce it. Makes it a little bit easier to understand. When we talk about this piece of the model, we're trying to measure the performance of the system. Now, I realize that word performance is very vague and it's going to be kind of an it depends answer. Within the context of networks, we're typically measuring the optimality of flows across the network. So I think Russ often calls it state versus stretch on how far off the shortest path are we taking traffic, maybe as a result of aggregation, maybe as a result of traffic engineering, which means in the case of aggregation, maybe it was undesirable, but in the case of traffic engineering, maybe it was desirable. So we're really just trying to measure the performance here without really paying too much attention to the other two. So we're very focused on that. This also could be a measurement of other components or other goals of a network. For example, our optimization goal is to optimize security. Maybe increase security would probably be a better way to say that. Or manageability, or any other piece of a network, or any other thing that matters. And even though we oftentimes in networking are focused on the routing and the flow of the traffic, these other things could be part of the process too, because I can think in my mind of some ideas where maybe if we add more stateful inspection to the network, we get better security, but of course there's more state and there's more service interaction, just to give one example. So security is a good example of something that could be optimized. The only restriction of things that cannot be your optimization metric are state and surface. So for example, you can't say, we want to optimize the network and our goal is to reduce state. Now, your goal can be to reduce state, but in reducing state, you're also going to probably increase your deoptimization or increase your surface interactions. So what we don't want to do is confuse the model by making the optimization metric one of the other two sides of the triangle. So I would encourage you not to do that. Otherwise, it just becomes really difficult to verbalize what you're trying to do. And it also becomes difficult to think about it. So let's look at some examples. Here's our favorite IntServe diagram again. Basically the exact same diagram, but now we're going to look at it less from a state perspective, but more from an optimization perspective. So forgetting about the fact that there's all this state in the network, I would consider IntServe to be a better optimized design with respect to the flow quality. I mean, every individual flow has its own special carved out bandwidth with specific requirements at every hop in the network. I mean, imagine when you go to the store to buy something or anything you do in your personal life, if every person you meet knew exactly what you as an individual wanted and could give you exactly the treatment you deserved, that would be amazing, wouldn't it? Yeah, but that doesn't scale. So we know that in real life, that's not how it works, but imagine if it did. That would be what I would consider a highly optimized design. Each individual flow has its network resource request honored by all devices. So I think that's pretty straightforward. Even when the network is highly loaded, this is still true. So even in situations of congestion, you can still get the optimal performance you expect. Now for diffserve, it's a little bit different. Now I'm not showing the diffserve diagram here because I don't think it's terribly important, but with diffserve, how do we deal with issues like congestion? Well, we have congestion avoidance. We can randomly drop traffic. We've got hop by hop QoS policies that we talked about in the previous one. I would consider that to be less optimal, wouldn't you? Think of it this way. The devices, again, we don't care about state, so just ignore the fact about state. If you go to the store and the clerk doesn't know you and they don't know what they want and they just see you as a customer that fits a certain profile, you get the treatment of that profile. And maybe that's good, maybe it's not. More often than not, though, is that your requirements are going to be a little bit different from the person next to you, even if you fit that same profile. So maybe they profile you and say, well, I think you're here to buy power tools, when in reality, that's not what you're there for. And you might need a different treatment because you went to Home Depot to get something else. So from an optimization perspective, IntServe is definitely superior. So now you can kind of see the trade-off. Now that we've examined at least two, or we've examined two out of the three different sides of the triangle, IntServe versus diffserve, and when you only look at the optimization component, IntServe looks really attractive. Now, of course, we know that in real life it's not very practical due to the state concerns, but you can clearly see the trade-off between the two, and it stops being a conversation of IntServe is worthless, don't do it, into I understand what IntServe is good for, but maybe it's not the right tool for me. And that's really the goal of this course, is to help you understand why things happened, how the networking history happened the way it did, and just some considerations about how you can objectively think about different protocols, even old ones that aren't commonly used. Let's move on to some examples that talk about what if we want to increase deoptimization. So effectively, this is a fancy way of saying we want to reduce optimization in order to reduce state. So let's think about this for a second. So the goal is to decrease state. So if we're trying to do that, we might do something like within a campus network, we might have a routed access design. For example, on the blue square is maybe our switch block. And again, I'm just using router icons because I don't want to make this overly complicated. I've got a couple distribution devices and then some access devices. And again, they're all running routing. Maybe I've got an OSPF stub area. So for those who aren't too familiar with OSPF, this is an area type where I'm just injecting a default route as well as all my internal OSPF routes. So I'll have longer matches for my routes in the green bubble and the blue bubble, but I won't have longer match routes for all my external destinations. So you can kind of see those. So imagine now that the router on the far right that says external destination 192, that one, when we do redistribution into OSPF, those two ABRs, the routers that are in blue and green at the same time, they're not going to pass on that external route into the blue domain. That means that the routers that are only in the blue area, in the stub area, are going to follow a default route through one or the other ABRs, and we can't really control which one they pick. Now, that's not really a big deal when we load share between them, because whether we go through the top or the bottom, they're both equal distant from the external router at the far right. But I can illustrate this better with the router at the bottom. Hopefully it's clear the suboptimality that may happen here. Again, we increased deoptimization specifically to decrease state. So we enabled this blue area for stub, knowing that it would decrease state, but at the same time, it made the network less optimal. Consider those routers in the blue area again, and they need to send traffic to external destination 203 dot whatever. They have a 50-50 chance of sending the traffic between the two ABRs, even though clearly the ABR on the bottom is the shorter path. So when we hide that information, we may get suboptimal flows, and in this case, suboptimal flows upstream towards the external network become the reality. We made this decision particularly on purpose because this is the problem we were trying to solve. Maybe we had too many external routes on all of our low-end access switches that were running layer 3, and it was just too much state for them to manage, and it was crashing them, something like that. So we might use stub areas to solve that problem, but again, we may have to have this trade-off with optimization. So we are deliberately reducing the optimization in this case. Just one example. Here's another example of we're reducing optimization, again, to use the terms here, to increase the deoptimization with the goal of decreasing surface interactions. This one's a little trickier. Consider that we have a company that's doing WAN QoS between its branch sites and out to the rest of the network. So that cloud just represents the rest of the network. Maybe we're following some design principles where we're doing classification and marking at the access switch, which is the switch. And we're doing queuing and traffic conditioning on the WAN router. So for example, when I say queuing, I think it's self-explanatory. Traffic conditioning, I mean shaping, policing, things like that. And then I'm doing congestion avoidance somewhere in the cloud. So maybe I have a self-owned MPLS network and I'm providing services for my own customers. Maybe I'm a large enterprise. I'm doing congestion avoidance there. So I've got this distributed surface interactions everywhere, and I'm doing QoS in multiple different places. Now, we haven't talked about surface yet, but if you can think about lots of dependencies now, because the router depends on the switch to mark the traffic properly. The cloud depends on the router to do the queuing properly so it can drop traffic in accordance with what the congestion profile looks like. Now, again, if this seems a little artificial, it is a little bit strange because a lot of times you tend to put multiple QoS features on the same device. But this is a specific example of very common design where people don't want that big surface interaction of spreading technology across multiple devices. So we may just consolidate all of it on the router. We might just say on the ingress LAN, I'm going to do my classification and marking. And then on my egress WAN, I'm going to do queuing, traffic conditioning, and congestion avoidance. So this one router is doing 5 different QoS functions. Now, we all know that's not that big of a deal. Those of us who have deployed QoS before, it's very, very common. But before we did that consolidation, we had this big surface interaction, which I'm going to call that more optimal because we're using the hardware-based classification marking in the switch. And again, doing QoS marking as close to the source as possible is usually desired. So that was a good optimization. And maybe spreading congestion avoidance out into the cloud, there might have been optimizations there if the branch routers didn't have the computing ability to do all those functions at the same time. So maybe we're decreasing optimization, reducing performance by consolidating it on one device, but at the same time, we've deliberately decreased surface interactions. So when your architect or your boss comes and they show you this diagram and say, hey, Joe, make it happen. And you look at this and you say, okay, cool, I'll make it happen. But then you think to yourself, in terms of the complexity model, what are the decisions that we just made? We decided to increase the optimization in order to decrease surface. So that's kind of the goal. And you just want to ensure that everyone understands that's what's happening. And this is a powerful tool to help explain that. In the next video, we're going to look at surface interactions. Personally, that's my favorite side of the triangle because there's kind of two dimensions to it. And I like to talk about that because when we talk about different components interacting together, things can get really interesting. So stay tuned for next time. Thank you.